Our next speaker is Tankut Zhang. So Tankut Zhang is from the Graduate Center of the City University of New York, and he will tell us about gating creates slow modes and control phase-based complexity in GRUs and LSTMs. Please, Tankut.
All right, thank you very much for the introduction. And it's a real pleasure to have the opportunity to share our work. So this is joint work with my collaborators Kamesh Krishnamurti and David Schwab. And it concerns the role of gating in recurrent neural networks and basically a physics approach to understanding what might be going on with these architectures. Okay, so first, what is recurrent neural net? What is a recurrent neural network? An RNN, they are interacting driven dynamical systems. And a classic example is the simple RNN, shown here in the gray box. Here, the hidden state H evolves by a nonlinear map, and it's driven by some input X. The output Y is a possibly nonlinear transformation of the hidden state. And the trainable parameters in this model would be the synaptic connectivity matrix U, as well as WH, which multiplies the input. And phi is nonlinear activation function. So we take it, for example, to be the hyperbolic tangent. And such neural networks are natural candidates to use in learning problems that involve processing sequential data. So sequential data with potentially variable length inputs and long-term dependencies in the data. So some obvious examples which might come to mind are natural language processing, as well as time series prediction or just fitting. However, a significant drawback of using RNNs is that when trained via gradient-based algorithms, such as backprop through time, they suffer severely from the exploding and vanishing gradients problem. And this is something actually that Shou alluded to in his talk. And I'll give an intuitive reason for this problem that really sets up our program of work in this paper. So you can get there, you can understand it intuitively by simply differentiating whatever loss function you choose for your problem, for your optimization algorithm, and applying the chain rule. And when you do this, you see that the gradient is weighted by the late time Jacobian, highlighted here in green, which is a product of many time-dependent matrices J sub t indicated here. And this J is the state-to-state Jacobian, so or the instantaneous Jacobian, if you will. And this is going to be the central object of our study. So the state-to-state Jacobian describes local or linearized dynamics, for example, around a fixed point. While the late time Jacobian describes asymptotic dynamics. For instance, it'll give you the Lyapunov exponents for the dynamical system. And this observation, tying the Jacobian to the gradients, inspires the following rule of thumb, which is just that if the spectral norm of J, of the instantaneous Jacobian, is less than 1, then you might expect vanishing gradients. And if the spectral norm is greater than 1, you can expect exploding gradients. And both are pretty harmful to training. So ideally, you'd want the norm to be close to 1, maybe even exactly at 1. Which means that perturbations will evolve very slowly in the dynamics of the system, and which puts you in a regime of marginal stability. So this appears to be a very fine-tuned condition and pretty difficult to achieve with a simple RNN robustly, which now brings us to the gating mechanism. So what is a gate? A gate is just a multiplicative interaction that provides a robust mechanism to controllably introduce long time scales and thus control gradients. And before I describe it mathematically, I'll just list some history of gating in RNN. So probably the first example of a gated RNN architecture is long short-term memory, and this is maybe the most popular example. And it's still widely used right now with only maybe minor alterations from its originally proposed form. The gated recurrent unit, or GRU, is slightly simplified. It's a variant of the LSTM, and it's also fairly competitive with LSTM, although on many measures, LSTM is generally more powerful. However, it's simpler and it yields a little more readily to analysis. So that's what we'll focus on in this talk. And I'll refer to our paper, our MSML proceedings paper, for more details on analogous results for LSTM that we have. Okay, so how do gates save RNNs, basically? How do they control timescales and thus control gradients? To understand this intuitively, we can start with the simple RNN, shown here, and couple it to an additional variable, which is given here by z sub t. And z is related to the hidden state by a nonlinear transformation, this sigmoid. So z will take values between 0 and 1. And u sub z here are an additional set of parameters that can be trained, in addition to u sub h, which was the synaptic connectivity matrix. So we can see when z is equal to 0, the simple RNN is recovered, the first term completely vanishes, and only the interactions are used to update the hidden state. Conversely, when z is equal to 1, the second term vanishes completely, and the hidden state h of t is just equal to h of t minus 1. So that it's not updated at all. And this allows, in principle, the creation of arbitrarily long-lived modes. And that's just the intuition for introducing this gate, which is just a multiplicative interaction. However, one can do much more with gates. The GRU also includes what's called a reset gate, shown here in orange, and labeled by an R. And this gate modulates the interneuron interactions and controls the relative strength of h of t minus 1 versus the input before it's sent through the nonlinearity phi. And phi, by the way, we're thinking of it as the hyperbolic tangent. That's throughout this talk what we'll be using. And since it effectively, the reset gate effectively changes the structure of the synaptic connectivity matrix, the reset gate will have an influence on the structure of critical points and on the overall network dynamics. So gating addresses the exploding vanishing gradients problem. It's actually seems to be a very good solution to this problem, but at the cost of introducing more parameters, leaving us clearly to navigate now a larger hyperparameter space. And this is practically challenging because in particular, training can still be terribly inefficient. It can still not really work out if we start with a poor initialization. For the GRU, for example, the initialization hyperparameters that at least we focus on in the paper describe just the overall scale of the connectivity matrices, which at initialization are just taken to be random matrices, random Gaussian matrices. Okay, so how do we optimally choose these hyperparameters? It turns out that we can look to the network dynamics for good initialization. Intuitively, what do we want at initialization? First of all, a wide range of timescales, presumably, including very slow modes to be able to adapt to variable time dependencies in the input. And also, as we mentioned before, we want the spectral norm of the Jacobian close to 1, or maybe just simply a lot of eigenvalues of the Jacobian close to 1, so that gradients will be well behaved. So both of these items point to the state-to-state Jacobian, which I introduced earlier, as an important object and a very useful object to study. And that's precisely what we look at in our paper. In particular, we wanted to understand in greater detail than maybe that been done in the literature before, precisely how gates will shape the spectrum of the Jacobian. And here, just a bit about the techniques that we use to get there. First of all, we needed mean field theory to determine, and this is all in the large network limit, we need mean field theory to determine fixed point variances of the hidden state variable. And these are the basic equations that we used. You can see the paper for more details, obviously. And these mean field equations are combined with some non-Hermitian random matrix theory to finally obtain a curve describing the boundary of the spectral support of the Jacobian. And that equation is on the left here, describing that curve. And also in the paper, but not in this presentation, are the spectral curve for time-dependent chaotic dynamics, as well as the analogous results for LSTM. Okay, so the first takeaway of our analysis is that the reset gate, in the absence of input, introduces really a distinct phase in the GRU dynamical phase diagram. And I'll explain exactly what we mean by that. So we can see this if we look at the fixed point solutions in the mean field equations as a function of two hyperparameters, AR and AH. And to remind yourself what those are, there's a little box summary at the bottom of the slide. For a sufficiently large AH, there's always just two fixed points. However, for smaller AH, there's a bifurcation at a critical AR where the number of fixed points abruptly jumps from 1 to 3. Hence the slogan at the top of the slide, reset gate bifurcates. At the microscopic level, this indicates an explosion in the average number or complexity of critical points in the n-dimensional space of hidden units. Now we can use the random matrix theory results to give us the stability properties of these fixed points. Obviously, that determines the dynamical properties, right? In the yellow region, all the fixed points are unstable, and really the only alternative is chaos, and that's indeed what's observed in the dynamics. So that's the chaotic phase. In the blue region, the fixed point is trivial, and it's stable, and all activity dies to 0. However, in the green region, shown here, which is only accessible thanks to the reset gate, and which is really just introduced due to the reset gate, there's a proliferation of unstable fixed points, and this leads to chaotic transients, which eventually flow to a single stable trivial fixed point. And remarkably, the update gate, which was this Z gate that controls the timescales, it does not influence the structure of the phase diagram at all. However, there's this really large region of the phase space, of the phase diagram, which is technically unstable, which is in this yellow region, but which the update gate can render marginally stable. And this occurs, strictly speaking, in the infinite AZ limit, which is when the update gate becomes switch-like. So ZT is just a binary variable in this limit, either 1 or 0. And this can be summarized in takeaway number 2, which is that the update gate promotes marginal stability. Our equation for the spectral support also reveals precisely how marginal stability comes about. The update gate, first of all, has the rather obvious effect of causing an accumulation of eigenvalues at lambda equals 1. And this just confirms the intuition which motivated the introduction of the gate in the first place. However, in addition to accumulation, there's a pinching of the spectrum at lambda equals 1, which is a little bit unexpected, and there's no reason to anticipate this just from introducing the gates in the first place. And lambda equals 1 is this marginally stable point. So the sequence of images here show the spectrum of the Jacobian, the curve describing the boundary of the spectrum as AZ is increased, illustrating how the leading edge gets pinched at lambda equals 1. in the limit that AZ equals infinity, one recovers marginal stability, as I mentioned before, and with a macroscopic number of eigenvalues exactly at 1. So as I said, also, the accumulation is generic, and it's also seen for the LSTM. But the pinching appears to be unique to the GRU. And this result suggests a novel initialization scheme in which the dynamics is poised both at the edge of chaos, which is sort of conventional wisdom and implemented quite often, and in addition to that, close to marginal stability. So large.
Just a heads up that you probably need to wrap up now. So you're running over for 2 minutes.
Yeah. Oh, right. So I just wanted to say one more thing. Also, in problems where marginal stability is somehow advantageous, this would suggest maybe GRU has an advantage over LSTM. But there's a lot to explore, and it's an exciting avenue for further research, I think. Thank you for your attention.
The first question for you is that, do you have some intuition from numerics or otherwise about how your work extends beyond the small step size regime to larger step sizes?
Maybe if the question can be clarified, I'm not sure. So we don't really have much to say about training. I can tell you that. Like, we have some experiments and a little bit of intuition, but as far as training is concerned, yeah, we're just working on kind of years of accumulated knowledge and intuition to inform our statements, as well as a few experiments. If by step size you mean like in the actual dynamical updates, I'm not sure. So for instance, a continuous time version of the discrete dynamics, is that? If that's the question, then there's a follow-up paper that should actually be out this week studying precisely continuous time GRU. A lot of results carry over. But there's also some interesting differences there.
Okay, thanks. Another question for you, for Tankut, is can you give some more details about what the edge of chaos is and the role this plays in your theory and for applications?
Yeah, absolutely. So we have these, we study these networks at initialization, which means we take all the parameters to be random variables. And when we do this, there's this sort of effective behavior that comes about. They can be described and they simplify significantly. And there's really only a few parameters that we can vary in the problem. As I mentioned, what they are really is just the overall scale of the random connectivity matrices. So this is a set of numbers, and for a fixed set of numbers, we can compute various dynamical properties of the network. So one thing that's possible to compute is the Lyapunov exponent, the largest Lyapunov exponent. And we can compute that as we tune the parameters in the problem. And what happens in these networks, typically large random networks, is that in some regime, the Lyapunov exponent is negative, so everything flows to a fixed point. But then when you cross some threshold, it's typically like a line in the phase in the space of parameters. The Lyapunov exponent crosses and becomes positive, and then you have chaos. So that's simply the definition of chaos, the positivity or negativity of the Lyapunov exponent. And the edge of chaos is just when really the Lyapunov exponent is 0. And typically it's a continuous transition, so it is actually 0 at one point. There's a bit of a subtlety that will show up in some later work where there's actually a discontinuous transition to chaos. That's related to what I was talking about, the reset gate. And that complicates edge of chaos, but that's the definition. And the motivation for thinking about edge of chaos and why it appears to be good, at least in practical applications, is that It has sort of to do with signal propagation. You can imagine if the Lyapunov exponent is very small, everything is, any signal will very quickly be contracted by the dynamics to some fixed point, and you sort of lose information very quickly. Similarly, if the Lyapunov exponent is very large, you're very chaotic, everything is getting get scrambled, and you similarly are not able to do any kind of useful computations. You want as long of a time scale as possible, presumably. And this is why edge of chaos is the best, because that's when lambda, the Lyapunov exponent, is exactly 0. So you don't have explosion or decay. This is related to the exploding and vanishing gradients problem as well. And in fact, it's intimately linked to it. So yeah, the gradients will also be well behaved there. So there's these two perspectives whereby edge of chaos is actually a good thing.